Welcome to Schweitzer Drive, a podcast where we explore what goes on between the generation of electricity and the light switch. Join Dave Whitehead as he interviews the entrepreneurs, innovators, and experts who are inventing the future of electric power.
Hi, I'm Nick Seeley, Senior Vice President of Engineering Services at SCL, and I'm sitting in for Dave Whitehead today. Historically, nuclear energy projects have been big in physical size, power, and megawatts, and also in cost. They've also encountered big challenges when it comes to getting new reactors built and brought online. Today, I'm talking with Brian Gitt of Oklo, a company developing next-generation nuclear technology, including a smaller nuclear reactor that promises to leverage existing technology in a new way. Brian leads business development for Oklo in Santa Clara, California. It's a startup developing advanced fission power plants to deliver reliable, low-cost, clean energy 24/7. Before joining Oklo, Brian spent more than 2 decades building companies in the clean energy industry, first as executive director of Green Building Trade Association, then as CEO of consulting firms specializing in clean energy. And more recently, he founded Utility Score, a software startup that estimated utility costs and savings for over 100 million homes. And then he's led business development at hard tech companies developing wireless power, and now he writes and speaks about the need for clean, reliable, and affordable energy. Brian, thank you for taking the time to talk with me on this podcast.
I'm excited. Thanks for having me on the show.
Yeah, excellent. We'll get right into it. Will you talk a little bit about Oklo, how it got started, its mission, and then one thing that I'm really curious about is where does its name come from? I assume that there's a story or background behind it, and I'm really interested in understanding more.
Absolutely. So Oklo provides clean, reliable, affordable energy through advanced fission power plants. And so we design, build, and operate these plants and produce and sell the energy, both electricity and heat. And that's a little bit different than traditionally nuclear reactor companies have done. So that's kind of what we do. And our mission is to produce as much clean, reliable, and affordable energy as possible. You brought up the origin story, which is really interesting. The name Oklo actually comes all the way from East Africa West Africa, in an area called Gabon. And this was from a natural fission reaction that happened in the Earth about 2 billion years ago. When most people think about nuclear energy, I think they think of artificial environments and humans and all of this kind of, modern infrastructure. But actually, fission process happened naturally 2 billion years ago in the Earth. Basically, there was just the right concentration of uranium ore and the active ingredient 235 and the right amount of water, and that acted as a moderator, and there was an actual natural fission reaction that happened in the Earth. And this was only just discovered in about 1972 in a uranium mine, and they just saw this kind of difference in the material there, and they couldn't figure out what was going on. And then further kind of exploration, they discovered this kind of ancient fission reactor. So it's just kind of an interesting story. And so the founders, Jake and Carolyn, named the company after this kind of natural phenomenon that happened a couple billion years ago.
And they call the natural phenomenon Oklo?
Yeah, the name of it. Well, Oklo is the name of the mine.
Oh, okay. I gotcha.
This happened in Africa. So Oklo derives its name from that location in Africa.
Where they found that. No, that's cool.
Yeah.
I was hoping for a good story like that. That's great. You're really focused on smaller reactors. Can you kind of share why? Like, why smaller? Because a lot of what we know about reactors is kind of like what I said in the beginning. Is like they're big, right? It's big power output. So why the focus on smaller?
Historically, there's 3 big challenges that the nuclear industry has really been faced with that it has to overcome. And those are high upfront costs, long build times, and then public perception around safety and waste. And so when Oklo was founded 11 years ago, Jake and Carolyn really wanted to think from first principles how to solve each one of those. And so the first one, high upfront cost, that has directly to do with the size. Because if you're building 1,000 megawatt huge plant, you're talking about billions of dollars. So on average, you're talking about probably $5 to $10 billion per 1,000 megawatt unit. Now, that's a lot of upfront capital, a lot of risk that someone has to take on. A utility likely is one of the only entities that's going to invest in something like that. And a lot of them are betting effectively the entire company on one mega infrastructure project, given the magnitude of the investment. So by going smaller, because we build two different size, we call them powerhouses, because we're really, the nuclear reactor is just one part, one component of the overall power solution. You have heat exchangers and you have your secondary plant with the steam turbine and the generator. The reactor is just a way to generate heat. It's just, I like to think of it as a fancy tea kettle, right? It's just a way to effectively create steam that then runs a normal steam turbine and generation process. So our powerhouses are 15 megawatt electric and 50 megawatt electric. And these are independent small little power plants that you can just kind of plunk next to each other, kind of daisy chain them together. So if you have, let's say, a data center campus that needs 500 megawatts, well, you put 10, 50 megawatt powerhouses. And this is very similar to what they do in natural gas. I mean, oftentimes you have a bunch of smaller gas generation units because you get to the level of redundancy and reliability. You can add more units. When you take one offline for maintenance, you have another one you can plug in and take over that capacity. And that's why the size matters a lot. So the reason why we're focused on data centers, factories, industrial sites, military bases, those type of applications are perfect. Number one, because of the size, like 1,000 megawatt reactor would be way too big. Even a lot of the the quote, small modular reactors are 300 megawatts. Well, that's too big for a lot of these applications. I mean, I was just on a call earlier today with a refinery, and I talked to chemical manufacturers, and they're looking at oftentimes per facility, they might have 70 megawatts of power, and then they have thermal heat requirements as well, or maybe they have 20, maybe they have 100, but 300 is too big for many of these applications. And even data centers, when they're building out a number of data halls on a large campus, they don't want one large power asset. It's a mismatch, because if you put, even let's say you have a gigawatt scale data center campus. Well, if you put a gigawatt reactor, which is the traditional size, next to that data center, what are you going to do when you take it offline every 18 months to refuel it? You're going to take that offline for a couple of weeks or more. You can't, that's impossible. Data centers need 5 nines of reliability, 99.999% uptime. So by going smaller allows you to add redundancy. You just add additional powerhouses so that you can deal with planned outages and maintenance and refueling and all of these real world considerations that these kinds of facilities that require 24/7 energy need. Now, large plants are excellent for utilities that are managing kind of a large area, a large service territory where they have lots of different customers and the demand is kind of going up and down over the course of a day and a month, et cetera. But they're not really well suited for a single large energy customer.
Yeah, a couple of things there I think are interesting. I used to do a lot of work with oil and gas, and in one of the things that I found interesting is in a lot of that process, like they actually don't care as much about the electricity as they care about the heat, right? So a lot of times what they produce is because they produce it because they need the heat. So I think it's really interesting. I didn't really realize you guys were actually doing both the electrical side, but that also the heat as a product for processes. So that's really interesting.
Yeah, just to piggyback on that, heat is a primary product. Actually, we're generating the steam before we even are making electricity.
Right.
So
yeah.
And this is really high quality steam. This is 420 degrees C steam, which can take care of a lot of applications in refining and various manufacturing processes. And oftentimes, they don't really have any other viable options if they want to cut their emissions. So this is really, obviously solar or wind is not going to solve for industrial heat in that way. So it's really one of the only clean sources of thermal capacity that they have available to them.
Yeah, that's really interesting. You also mentioned, as you started talking about this at the beginning, a little bit about public perception. And one of the things, like, you're trying to go back to first principles to try to understand public perception. And so how are you doing that? Like, what are you thinking about to try to, make nuclear seem, unfortunately, it seems like really scary to a lot of people, and for good reason in certain circumstances, right? You got, Chernobyl that people are aware of, but what direction are you going, and how are you thinking about that?
The public really cares about two basic things when you talk about nuclear energy. Obviously, customers care about cost and schedule, et cetera, but from a public perception perspective in the surrounding community, they care, is it safe? And what about the waste? Those are really the two primary issues. These particular designs are what I would consider meltdown proof, meaning it's physically impossible for them to melt down, and they self-cool and self-regulate using natural forces. What I mean by that is you don't need backup power. You don't need motors or pumps or mechanical systems. You don't need human intervention. So in the worst case, catastrophic natural disaster, fire, hurricane, flood, earthquake, whatever that scenario, we're even putting these on military bases where we have to consider, what if an adversarial country launches a missile and tries to blow up the powerhouse? I mean, or what if a commercial airliner crashes into the powerhouse and takes it out? Like, these are all real scenarios that we have to document what happens in those scenarios. And in all those scenarios, there's never a risk of any radiological release, which is what people are concerned about, beyond the site boundary of our power plant. So now contrast that. So if you take a 50 megawatt electric powerhouse, that sits on 1.5 acres of land. That's it, 1.5 acres. It's tiny for 50 megawatts of power. Now, the first one, you have a parking lot and it's a little more, it's like 3 acres. And then every additional powerhouse is 1.5 acres. So if I was using that example of a 500 megawatt data center campus, you got 10 of them. So the first one takes 3 acres, and then all of the additional ones are 1.5 acres. Now, our emergency planning zone for that is the actual that 1.5 acre site boundary for the powerhouse. There's no setbacks. There's no buffer zones of land required. Now, contrast that to a large light water reactor. We have 94 operating light water reactors in the United States. Those require approximately 10-mile emergency planning zones around them. Now, those are perfectly safe. I mean, I think 70 years of safe commercial operation, I would argue it's, if not the safest, certainly one of the safest industries we have out there in terms of track record. Compare that to other industries, it's almost unheard of, right? I mean, we've had one accident in the United States, 3 Mile Island, and no one got hurt. There was no human health impact of it. The amount of radiation that was released out of that is the same as you and I going on a hike in Denver in a Saturday afternoon. So there was no human health impact. So that's all saying the existing plants are safe, but these are next level because you don't need complex backup safety systems because they just use natural forces to self-regulate, meaning gravity, thermal expansion, and airflow. So you don't need backup power, you don't need humans to do anything, and you don't need any kind of pumps or mechanical systems for safety. That's a really critical thing. So once people understand there is no risk to the surrounding community for radiation release, then that concern around safety is off the table. Now, there's other reasons people are against building things, right? There's lots of NIMBYism, not in my backyard. People don't like anything built in their backyard. So I'm not to say that there's no opposition to building any kind of power infrastructure, but that's true with natural gas, that's true with solar, that's true with all kinds of energy sources. The other thing is the waste. So we recycle spent fuel. What most people call nuclear waste is not really waste. It is just used fuel. And the reason why it's an important differentiation is because we have about 90,000 metric tons of used fuel in the United States that are sitting around the country, mostly at these sites where either there's an active nuclear reactor or there was one in the past. And if you were to put all of that fuel in one place, and put it in a building, it would all fit after 70 years of commercial operation. It would all fit in one Walmart supercenter. So although it's heavy, right, because it's 90,000 metric uranium on the, remember the periodic table, it's all the way down on the right.
Mm-hmm.
It's a very heavy element, but from a volume perspective, it's tiny. I mean, 20% of all of the electricity in the United States for 70 years approximately the waste from that fits in one Walmart supercenter. And here's the best part about it, that 90% of the energy is still in it. This is what is really the big unlock, the big opportunity. We can recycle that spent fuel and turn it into new fuel that goes into our powerhouses. And we're doing this today, and we're developing a full-scale recycling facility to do it at scale in the very near future. And if we were to just take that 90,000 metric tons of spent fuel sitting there, that's enough to power the United States at our current level of power consumption for the next 150 years of having 24/7 clean energy for 150 years, just by taking that spent fuel and turning it into new fuel for advanced reactors.
My understanding is that it might be new in the US, but other countries have been doing that for years, like reprocessing the spent fuel and recycling, essentially. Is that accurate?
Yes, in France, they use a different process. They use a process called MOX, and we use a process called pyroprocessing. I'm not going to go into the technical weeds here today. They're different, but the result is basically similar, that you're recycling the waste stream. You're creating circularity within it. And there's different approaches on how you do it. Our approach is relatively simple. I mean, you basically take out the used fuel out of an existing reactor. They're in fuel assemblies. You undo the fuel assemblies. You take the basically the little pellets of oxide fuel out. You break it all up. You throw it in a salt bath, in this big bath of liquid salt. You run electricity through it. You have an anode and a cathode similar to a battery. And then that electricity helps separate the usable from the unusable elements. And then you basically scrape off the usable elements, and you recast it and turn it into new fuel, and you scrape off the unusable elements and you put in a safe storage. So it's a very relatively straightforward process.
You're describing a little bit about the reactor, and could you explain a little bit about how this newer design is different than traditional designs? So a lot of people are familiar, and you mentioned like the big 1,000 megawatt reactor, like light water reactors or whatever they may be, whatever technology they're using. How is what Oklo is developing? How is that different other than just being smaller?
So there's the size, which we talked about. Then there's the coolant, or the heat transfer fluid that we use. We use a metal. We use liquid metal. It's like a molten. It's a hot metal. It's sodium. That is instead of water. When you think about this from first principles, there's three ways that nuclear reactors use to basically transfer the heat from the fuel to basically the process to create steam, right? So you can use water, you can use gas like helium gas, or you can use metal. We use liquid metal. And when you think about it from first principles, metal is better than gas or water at transferring heat. It's actually 10 times better at transferring heat than water, right? So it's very efficient, which means you don't need a huge amount of concrete and steel for civil works to have a massive, basically a swimming pool for all that water, right? And that's part of the Achilles heel historically of these large projects, is they just take an enormous amount of concrete and steel. And it's actually the civil works where a lot of the delays and on schedule and cost overruns have happened. So if you're basically pulling out a lot of those civil work, we have obviously some civil works, but it's not really safety related. It's not extensive. In part of that is due to the decision to use a metal coolant, right? It enables us to operate at higher temperatures and then operate at atmospheric pressure. So there's no real pressure in that vessel. Which also has significant cost implications. So if you think about it, if you have a non-pressurized vessel and you have a certain size that it doesn't need to be forged, like a lot of the light water designs, they're pressure vessels, they have to be forged. And because they're so big, they have to be forged in South Korea or there's only a few places on Earth that you can make something that big. So our vessel size, basically just imagine a big tank, like a big stainless steel tank, similar to what you'd see in petrochemical or other industries. Because this is rolled steel, it's not forged, it's 316 stainless, it's very common, available alloys, nothing's exotic. This is very common kind of tank, right? I mean, obviously we're modifying it with some of the instrumenting it and the things in it are different, but the tank itself is not that unique or different. So all of this has huge implications on cost. So the choice of the coolant using metal impacts the cost of the reactor vessel, the safety case, how much concrete and steel you use. All of these things have ripple effects. Because we operate at higher temperatures than a traditional light water reactor as well, we operate at 420 degrees C. Well, now that's very similar to a fossil-fired plant. So now we can leverage an existing supply chain of steam turbines. So we partner with Siemens Energy as an example, and we're operating at very similar temperature as their kind of existing supply chain. So now, I mean, each steam turbine is dialed in for the use case, obviously, but they're not building anything customized or bespoke for us. We're able to leverage that existing size and existing parts and components supply chain. Whereas light water reactors, they only build those for 1,000 megawatt units. So that means to do something at that temperature is custom, it's bespoke, it's different. So you can start to see all these things add up. You got a lot more concrete and steel and civil works. You got pressure vessels that need to be forged in very remote, rare places on Earth. You have basically all of these other conditions that add cost. You have a pressurized system. And think about it. Everything that's pressurized is going to cost more. All the components and all the valves, all of these things make a big difference when we talk about cost.
We were talking a little bit earlier, we were talking about, you were talking about the data centers and the need for 24/7 reliable power and things like that. And traditionally what I think of nuclear power plants is they're running their base load, right? So they're just, you set them at a level and then they go at that level. Is that the same for these particular generators, these reactors, is that you want to set them at base load, or is there an ability to do also like peaking as well?
From a technical perspective, we can load follow and we can ramp up and down. However, from a business perspective, it just doesn't make a lot of sense to do that. I mean, generally, you're looking to these for baseload power. These need to really be operating 90% of the time or greater, just from a business case perspective. Now, we can load follow. We can ramp, 5% a minute. We can go up and down. We can go all the way down to 30%. There's nothing technically that prevents us from doing that. They're actually very adaptive. But it just doesn't make sense from a business case perspective. And the kinds of loads that we are targeting, like data centers and factories and industrial sites, those, for the most part, have pretty consistent, steady 24/7 loads. Now, obviously, a data center in the summer in Virginia, where they're having to ramp up their air conditioning load, their cooling load you're going to have some peaks and valleys, obviously, seasonal differences. But generally, we're going to target that base load, and then we can bring in storage, battery storage, and other forms of storage to deal with peak. You can use the grid as a backup or for peak power. So we're just taking care of base load, and they're using the grid for peak. There's all different kinds of strategies that can be employed to deal with those fluctuations. And it really just depends on the requirements of the site and what they need. We can also provide N+1 or just additional redundancy and have on these larger deployments. So we have an additional powerhouse. So we have, in essence, spinning reserves right there and additional capacity that we can use for different purposes as well.
We recently talked to a gentleman, his name's Eric Williams, from a company called TerraPower, and they're using a natrium reactor, I think natrium reactor, and they're doing a project in Wyoming. Are you familiar with that? And do you know, could you explain the differences between what you all are doing at Oklo and what TerraPower is doing?
Yeah, very familiar with TerraPower because they are actually using a very similar technology. They are a sodium fast reactor, sodium metal. That's the moderator. I'm sorry, not the moderator, the coolant that we're using. And that's the same basic reactor design as we are. Now, the biggest differences between what Oklo is doing and TerraPower are a couple things. One is just the size. So TerraPower is building much larger, hundreds of megawatts in size, over 300 megawatts in size of their reactor. Again, we're building 15 and 50. So it gives us a little bit more flexibility to ramp up and down. It's easier for us to have N+1 kind of redundancy. It's much harder to have 350 megawatts and then have a whole nother one, in terms of making that economical. So those were mostly designed to replace coal plants, which is great. This really highlights, I think, something that's really important. There's a whole ecosystem of nuclear reactor vendors out there that are building different sizes with different traits and characteristics for different applications. So, for example, their target customer is the utility, and our business models are very different. So they have a more traditional business model in the nuclear space where they license their design to a customer, typically utility. It doesn't have to be, but generally that who's historically been licensing those designs. And then the utility is owned and operating, or maybe they're partnering with a third party that's going to operate that facility. Well, our business model is we design it, we build it, we operate it. It's a very different business model, and our size enables us to scale down and then have that additional redundancy. One of the things that TerraPower has that we haven't baked into the inherent design is they also have a storage aspect of an energy storage aspect of what they're doing. That's kind of core to the product. Now we can bring in partners with storage as necessary, but it's not a core part of the product offering that Oklo builds and provides. Whereas they offer an additional kind of molten salt storage as a inherent part of the product.
Yeah, you mentioned in maybe just probably don't want to go too far into the weeds, but you mentioned something a fast reactor. Could you just give a very high level, like what is a fast reactor?
Simply, it's operating in a fast spectrum, so you don't use a moderator. You're not slowing the neutrons down. So oftentimes the traditional large light water reactors, they use graphite or some other moderator basically to slow that fission reaction down, whereas a fast reactor doesn't use a moderator. And so it's just going at a much faster speed, right, in terms of the fission reaction. Now, there's advantages to fast reactors in terms of fuel, and this is why partially we can utilize recycled fuel or fresh fuel, because partially due to the inherent characteristics of being a fast reactor. So there are advantages to this overall as well.
Yeah. Okay. I think that makes sense. Thank you for keeping that at a level that I can understand. One of the things we're talking a little bit about the public perception in kind of like fear of nuclear reactors, and then also the safety in terms of the waste things. So you talked quite a bit about that, and I guess I'll take this question a little bit further because I'm interested in some of the folks that you talk to that are really into like environmental conservation and are really concerned about the environment. They have taken a stance where nuclear is still it's bad, right? And they don't. And obviously they have reasons for that. You have, you are obviously committed to this area of environmentalism, but you have gotten to the point where you think nuclear is good, and you think it's really a solution to a problem. I guess I'm just curious, how did you get there, and why do you think there's the difference between the folks that are equally committed to a cause of environmental conservation, but some are really for this and some are really against this? I'm just curious.
Well, I think first, if we think about this from first principles, the materials intensity of an energy source ultimately is going to have the biggest outsized impact on its environmental footprint. So what I mean by that is for every unit of energy you have to invest to create that technology, and you get X amount of units out. So with solar, for example, the energy return on energy invested, you put 1 unit in, you get about 3.5 units out. With nuclear power, you put 1 unit of energy in, you get 100 out, right? And so that has massive implications in the materials intensity. So how much mining you have to do, how much transport and diesel fuel you have to burn to deal with all of those raw materials and turn them into various products and ship them around. It impacts how much land in terms of the land footprint. And the more land that you need, obviously that's less room for nature. So you're just ultimately going to be destroying more habitat when you're using more land. And then in addition, you're going to create more waste, right? Because you have more surface area, more minerals, more materials. So when you look at it through the lens from an environmental sustainability lens, nuclear power, hands down, is the cleanest way to generate 24/7 energy. There's nothing that even comes remotely close to it. Even on CO2 metric, it is significantly less CO2 life cycle emissions than solar, as an example. So any of those metrics that you choose, now the concern is really historically has been around the waste. But as I mentioned before, we can recycle the waste, and we are looking to recycling the waste, not just conceptually. We're actually in pre-application right now with the Nuclear Regulatory Commission to build a full-scale recycling facility in the U.S. to take that used fuel that I talked about earlier and turn it into 24/7 clean energy. So this isn't just theoretically it can be recycled, it actually will be recycled. So that really historically has been the one point that environmental groups have pointed out of concern. And I would say it's not the problem at all. It's actually, arguably, it's a gift to future generations because we have all of this raw energy at our disposal that we can convert into a 24/7 resource.
Yeah. And so Oklo is actually, I believe what I've read is you said that you're trying to bring the your first small nuclear reactor plant into production or into operation by 2027. And maybe you could speak to that. And is there the reprocessing? Is that part of that will go into production by 2027 as well? Or is that here now, or is that a longer term?
So our first unit at Idaho National Lab will actually be using recycled fuel. So we have a building there right now, and we're in the contracting process to take spent fuel that ran the actual design that we're commercializing. It was called EBR2, Experimental Breeder Reactor 2. It ran for 30 years, from 1964 to 1994 at Idaho National Lab. It was a 20 megawatt fast reactor using a metal coolant, just sodium metal, just as we're using. And they also recycled fuel. They demonstrated that capability at that particular plant. So we're taking that fuel and recycling it for the first one. Now, we will be using fresh fuel for some of our subsequent units until our recycling facility comes online. And that facility won't be online until towards the end of the decade. So I foresee that we will need to access fresh fuel and recycled fuel as much as we can get our hands on both for the foreseeable future. So I'm not trying to position that we're only going to be using recycled fuel in the near term. Now, eventually, hopefully it's to our economic interests to use as much recycled fuel as possible, because we can save up to 80% on our fuel costs by continuing to recycle that material through that process and taking it out of a powerhouse after 5 to 10 years, putting it back through recycling and doing that multiple times. So there's a financial incentive for us to do it, as well as just an environmental benefit of doing that.
Yeah, no, I definitely see that. So you've got your first reactor coming online at Idaho National Labs. It sounds like you're going to have the recycling process by the end of the decade. And then if we look further out, if we look out 20, to 50 years, like where do you see things going, and where do you see nuclear power?
Well, obviously I'm biased. I mean, but
that was a softball.
So I am not, but it's kind of reverse what most people think. So I used to work in the renewables industry and energy efficiency programs, et cetera. And the reason I got into this was because I felt that nuclear power was the best solution. It was very much coming from a mission perspective. That's why I chose to work at Oklo. It wasn't like, oh, I have a job, now I got to go promote that technology. It's just the opposite. I really feel that the future is clearly inevitable, that we've been moving historically from lower dense sources of energy to higher dense, more concentrated sources of energy. That's the entire human evolutionary story that, we started with wood in various renewable energy. We started with wind and sun and wood, and then we moved to coal, and then we moved to oil, and then natural gas, and then up to nuclear. As we went up that evolutionary curve, we went to more concentrated and denser forms of energy. Nuclear power is the apex. There's, maybe in the future we'll even figure out something even more dense, but as of now, in terms of what we know, that is the best we have access to. And the reality is there's enough nuclear fuel on planet Earth today. If you just take the existing stores of known uranium as well as recycling and factor that in and using advanced fission, like the technology we're doing, we have basically limitless energy for about 4 billion years, which at that point, the sun will destroy the Earth anyway. So we have all the energy we need for at least 4 billion years. So we're not going to run out anytime soon using this energy technology. And it, again, has the smallest environmental footprint for the most amount of power and overall heat energy.
Besides the sun going supernova, like what concerns you about the progress of nuclear energy? What are the hard things?
We have challenges, and I'm not trying to present that this is just a clear path and we have no challenges in our way. Our biggest near-term challenges are fuel supply chain bottlenecks. So over the last several decades, we've outsourced a lot of our uranium enrichment capacity to Russia and to other countries. And just recently, the United States have banned imports of enriched Russian fuel. Now, there is a grace period, obviously. This is even for the existing 94 operating reactors in the U.S., as well as all the new advanced reactors and SMRs. So this is spurring the United States government is putting $3 billion into building out more domestic enrichment, and as well as companies are investing. Just about a week or so ago, Orano announced a big project for uranium enrichment project in Tennessee. We have Centrus Energy in Ohio. We have Urenco in New Mexico. There's all of these facilities are going to be building out more capacity, but it takes time. It doesn't happen tomorrow. So we need a few years for that capacity to be expanded. And then we need a few years for our recycling facility to be online. So in the short term, we do have fuel bottlenecks, and it is constraining our ability to deploy at full scale over, let's say, the next 5 or 6 years. We will be deploying, but it just will have some limiting force. Yeah. But once we hit the early 2030s, I think that's really going to open up, and all of that capacity will start to come online, and then we won't have those bottlenecks. The other challenge is regulatory. So getting through the Nuclear Regulatory Commission has been very hard. We've been formally engaged with them since 2016 and iterating our way through and making a lot of progress. And we're kind of towards the tail end of this process now after, 8 years of effort. But it has been a long road, right? It's not an easy thing. Mm-hmm. And part of the challenge is that the history of the regulator is working with light water reactor designs. They're not working with metal coolants and different fuel types, et cetera. So there's breaking new ground aspect to this, even though the technology is proven and it's established. And actually, this design was first developed in the 1950s. And there's over 400 reactor years of operational history around the world. About 25 of these plants have been built. However, our regulator still needs to get comfortable with a lot of these things. So it takes time. So those have been two challenges that we have been navigating: is fuel supply chain and licensing and regulatory.
Brian, thanks for that. It definitely sounds like you all have your work cut out for you, but I've got every confidence that Oklo is going to be able to figure things out, and I'm looking forward to seeing what you guys are going to be doing in the future. It's been great talking with you. I really learned a lot, and I really appreciate the time that you spent with us. So thank you very much for coming on the show.
Thank you. Appreciate the opportunity to come on.
Thank you for stopping by Schweitzer Drive. Join us again as we learn about, explore, and celebrate electric power. For more information about the show, please visit selinc.com/Schweitzer Drive.